Değerli katılımcılar, sevgili arkadaşlar, ülkemizin bilim dostu, bilgisever, güzel insanları, herkese iyi akşamlar. Bilindiği üzere bugün ne yazık ki ülkemizde ve dünyada pandemi süreci hız kesmeden devam etmektedir. Zalim hastalık, Türk insanı da dahil olmak üzere milyonlarca insanın dünyasının değişmesine neden olmuş, insanlığı derin üzüntüye boğmuştur. Bu süreç aynı zamanda dünyada insan ilişkilerinin sorgulanmasına ve yeni bir boyut kazanmasına yol açmış, insanoğlunun dayanışma ruhunu güçlendirmiştir. Bu süreçte bilimin ve temel bilimsel düşüncenin hayati önemi bir kez daha büsbütün olarak ortaya çıkmış, bilimin insanlık için en büyük özgüven kaynağı olduğu bir kez daha kanıtlanmıştır. Antik çağdan günümüze kadar daima var olan bilimin insanlık için birleştirici özelliği pandemi sürecinde daha da kuvvetlenmiş ve yeni bir boyuta ulaşmıştır. Buradan hareketle TÜBİTAK Temel Bilimler Araştırma Enstitüsü, dünyanın önde gelen bilim insanlarının işbirliği ve katılımıyla ilham verici, çevrim içi seminerler serisi düzenlemektedir. Enstitümüz bu bilimsel eylemleriyle ve derin bir dayanışma ruhuyla en üst düzey ve yenilikçi bilgileri ülkemizin bilim ve eğitim camiasına aktarmaktadır. Bu akşam yine bu vesileyle ve bu sefer kimya bilimleri seminer serisi kapsamında bir güzel bölüm daha gerçekleştirmek üzere bir araya gelmiş bulunmaktayız. Ben de bu vesileyle hepinizi saygı ve sevgiyle selamlıyorum. Bu akşam Kanada'daki Toronto Üniversitesi'nden son derece değerli bir bilim insanı, Profesör Andrei Yudin'den kimyasal sentez araçlarını kullanarak bioaktif moleküllerin geliştirilmesi konusunu dinleyeceğiz. Seminerimiz İngilizce olarak gerçekleştirilecektir. Dear Professor Andrei Yudin, dear participants, dear colleagues and friends, a very warm hello everyone. It is my sincere pleasure to welcome all of you for this inspiring online seminar series of TÜBİTAK Research Institute for Fundamental Sciences, which we organize for national and international audiences. It is also my distinct pleasure to inform you that this evening we will have another wonderful episode of our Chemical Sciences Seminar Series with the participation of a world-class expert in the field, Professor Andrei Yudin from the University of Toronto, Canada. He has kindly agreed to join us for this seminar, and he is going to give a great talk. Development of bioactive molecules using the tools of chemical synthesis. At the end of the talk, we will have a question-answer session where questions can be asked by sending a message through the chat button of Zoom platform or just by raising hand. Professor Yudin's group is well known for the development of new tools for chemical synthesis. In recent years, Yudin and his students have pioneered the chemistry of molecules that contain reactive and usually incompatible functional groups. This concept of force orthogonality has enabled his lab to develop entirely new synthetic processes based on unprotected aziridinaldehydes, now commercially available through Sigma Aldrich. Professor Andrei Yudin is a Tier 1 Canada Research Chair in Medicine by Design at the University of Toronto. He obtains his Bachelor of Science degree at the Moscow State University in 1992 and his PhD degree at the University of Southern California in 1996. He subsequently took up a postdoctoral position in the laboratory of chemistry Nobel laureate Professor Barry Sharpless at the Scripps Research Institute. In 1998, he started his independent career at the University of Toronto. He received early tenure, becoming an associate professor in 2002, and received an early promotion to the rank of a full professor in 2007. Currently, one of the main focuses of research in the Yudin group is to develop a bridge between basic chemistry research and drug discovery. With this, I want to invite Professor Andrei Yudin to the stage to begin his talk. Andrei, good morning. We are honored to have you with us. Please begin your talk.
Thank you very much. Let me first start by, can you see the slides?
Yeah, it's okay.
Excellent. Thank you very much, Alikram. And I would like to thank you and, of course, everybody who is participating in this. Still kind of we're still getting used to this format, but it is really the one that we have, and it is great to be able to present in Turkey, and I really look forward to visiting you in person, hopefully next year, and meet everybody. So today, I would like to demonstrate, I suppose, how basic, and should we say fundamental, thinking about chemistry is helping us develop novel molecules. I'm going to start with something that is very, I would say, important for my lab right now, and it's a new area, and it is what we call synthetic half reactions. The concept itself was covered by me last year, and I would like to very briefly introduce it because it does set the foundation for some of the things I will discuss later. So first of all, we as chemists are familiar with half reactions only in electrochemistry. It's a very powerful tool. For instance, we can easily demonstrate that zinc cannot be reduced by copper, but copper can be reduced by zinc. And this is on the basis of standard electrode potentials. Well, of course, in the case of these kinds of electrochemical reactions, we have another body, which is an electrode. Everything is referenced to it. And in synthetic chemistry, we actually don't have it. However, we thought that perhaps there is a way of thinking about this. I will present this way of thinking in a very artificial manner because you all know electrophilic aromatic substitution. But we can also say that it is a match between an endergonic disruption of aromaticity, we call it N-type, and exergonic restoration of aromaticity. And in some way, we can consider that what we call spatio-energetically, these two half reactions are matched in electrophilic aromatic substitution. And of course, as you can imagine, I didn't need to do it for this process because you know it quite well. But the very interesting question is, as synthetic chemists, have we exhausted all combinations of driving forces and difficult steps? And I think the answer to this is no. So we set out to ask this question in a variety of fields, including conformational analysis of maybe complex molecules. And in this particular case, one of the things that I think is very intuitive to a chemist is that if you want an energetically releasing exergonic process to influence endergonic process, they need to overlap. So, and this degree of footprint is actually something that, again, intuitively is familiar to chemists. I'm going to demonstrate it using conformational analysis. And this is, I think, is a very interesting example. If you have chiral piperidine, there is a way, and medicinal chemists use this quite often, to make sure that you have a molecule with axial substituent. This particular product is going to be favored in this conformational equilibrium. In the language of what we have right now, it is a match between endergonic placement of the R1 group in an axial position and the driving force of release of allylic strain. And interestingly, of course, if you have a distance between these two, there is not going to be any appreciable concentration, should we say, of R1 in an axial position. And so these principles teach us how rotations in molecules are coupled. And I think that one of the best ways of thinking about this process is in the context of a cyclic peptide or a macrocycle. It's a fantastic and very complicated molecule. And first of all, it is difficult to synthesize. And so one of the things early on that we took upon us as a challenge was to develop new methods of making macrocycles by taking linear peptides. Interestingly, they are quite often pre-organized to be cyclic through this zwitterionic interaction. But then synthetic chemists usually remove this by making a neutral carboxylate derivative, and then you kind of have to climb through the same barrier again, which is, I think, very counterintuitive. So in order to help us, we have developed over the years a wide range of fairly unusual molecules. And these are amphoteric molecules where some kind of a kinetic control allows orthogonality between a nucleophile and electrophile. You can see that, in fact, and this is our classification, this is an old concept in some way, but it's just that there are not many molecules that are synthetically useful and kind of abide by this principle. Isocyanide is one of them, carbene. But we, throughout the years, introduced these kinds of structures where we have, I would say, fairly unusual combination of properties, because, for instance, we have a nucleophile on an electrophilic center. This is alpha to an electrophilic center. And then, of course, I'm going to speak a lot today about the aziridinaldehydes. The way we came to realize this concept is through learning a little bit and reminding ourselves about Stork enamine synthesis. That, of course, is very well familiar, I'm sure, to many of to all of us, right? It's a very familiar concept. And the key intermediate is this hemiaminal that is being obtained when pyrrolidine attacks the carbonyl group. And then, of course, there is very well understood imine information, enamine, and so on and so forth. And so what we were drawn to is this realization that some hemiaminals, in this case, aziridine-based hemiaminals, actually can be quite stable, because the iminium ion is going to be high energy due to strain. And it took Ryan Healy in my lab some years ago now, a while back, to take wine-herbamides of this type. And Ryan discovered that you can produce this unprotected aziridinaldehyde that, upon workup or aging, is going to dimerize to generate this unsymmetrical system. And so it's a white solid. This was a surprise because unprotected aminaldehydes are not supposed to be stable. But what happens here is, again, you form hemiaminal, and instead of forming iminium that is high energy, it undergoes rapid collapse with this OH attacking the aldehyde, and this is what we eventually isolate. And so these molecules throughout the years have allowed us to generate interesting compounds based on interception of intermediates. So this is a very nicely, I think, exemplified in this Pictet-Spengler-like process where we are intercepting one of the key intermediates because we are able to place nucleophilic NH-aziridine in its close vicinity through the action of some of these dimeric species. And then, of course, mechanistically, we have established that monomer that is produced here rapidly redimerizes. And in fact, there is quite a number of reactions that have this logic where dimeric aziridinaldehyde somehow orchestrates the events that correspond to bond formation in the near vicinity. And it's actually fun to think about this as a catalytic cycle, if you will, because rate limiting is typically opening of the dimer, then activation by substrate, and then redimerization. This is where we typically would spin, so to say. But how does this all relate to cyclic peptides and macrocycles? Well, in terms of discovering new reactions, one of the aspects amphoteric molecules can offer is the idea of taking a known process. And if you can find an intermediate that can selectively interact with one of these two nodes, you can literally direct this process to a new outcome. That is disruption. We can also see potentially the possibility for cooperativity between two known amphoteric molecules. And this particular case was very interesting to us because it's like having isocyanide, which is of course very well understood, and then our novel aziridine aldehydes, and asking this question, what can they do together? And what they can do together is shown on this example, because what we took is we took a very standard UGI reaction with isocyanide that produces this mixture of diastereoisomers, and then we mixed as a control, kind of a, let's say, competition experiment, our aziridine aldehyde dimer. And the benzaldehyde was not incorporated in the product. Instead, we now have this very exciting, unusual looking compound that literally was the first sort of a step in our growing appreciation of cyclic peptides. Because of course, through the action of these bifunctional compounds, we were able to hypothesize that we can potentially capture this very elusive ring chain equilibrium and enable the hydrogen bonded assemblies to eventually close the ring, such that we are effectively solving the problem that exists in peptide macrocyclization by using an intermediate that is inherently able to link the two termini together. And so this is how this then evolved. In the presence of an aziridine aldehyde and isocyanide in trifluoroethanol, we were able to take peptides and convert them into these cyclic versions with aziridine ring at fairly high concentration. And that was again because the ends of the chain throughout the mechanism remain in close proximity. And so it's literally something along these lines where you are effectively using the inherent inability of aziridine to form imine. Instead, this aziridine aldehyde with an aldehyde functionality is going to form this imine. And as you can see, these hydrogen bonds, we believe, they play a role in recruiting the right conformation that through the action of hydrogen bonds eventually brings carboxylate in the proximity of this iminium. And then what takes over is what is very well understood in UGI reaction, except the last step is very, very different because our aziridine through the hemiaminal is going to attack this carbonyl and lead to the formation of the macrocycle. And so it's actually kind of an interesting transition state that operates presumably here. And I have to also admit that there is a substantial role for trifluoroethanol here, because in methanol, this chemistry doesn't work. Methanol is too nucleophilic and it reacts with a mixed anhydride, whereas here, aziridine is allowed to react with the mixed anhydride before solvent can come in. What do we do with these structures? And I think this is what I'm trying to kind of build up to right now. This aspect of structural organization and understanding folded structures of this complex type has been our goal for now many years. I would like to demonstrate to you how we typically go about understanding these compounds. So this is the isocyanide that is shown in blue. Upon macrocyclization, you are producing these blue amide bonds that, as you can see, are exocyclic. So they're not part of the macrocycle. They are attached to the macrocycle. And this is that pivotal aziridine, right? Acyl aziridine that, for all intents and purposes, is not your typical amide. This barrier to rotation is very low, so it's almost free to rotate. And I would say, as such, this is conformationally very flexible, fluxional system. But if nucleophile opens up, for instance, this is a hydride formally nucleophile, then you produce a folded structure where you see these red bonds, these red dotted lines. They signify intramolecular hydrogen bonds. And this network of intramolecular hydrogen bonds I think is to a large extent maintained by way of these exacyclic blue bonds. This is X-ray in solution, slightly different structure, but still we see that there is this dominant interaction, and these are the ppb per Kelvin, so these are chemical shift changes that we usually use in order to understand these structures. I also note that hexacyclic amide, the likes of which we see here, is actually not present in natural amino acids, right? But and this actually is a very interesting control element. But you have to remember that there's a reason why there are no amino acids of this type, because of course this is a fairly unstable structurally and configurationally substructure. And so, but in our case, it's peptidomimetic, and that is the key. We don't have carbonyls nearby. We have looked at other methods. We introduced not too long ago boronate-driven macrocyclization, where we effectively capture pitacesis reaction, where we generate imine and then let boronic acid attack. And so these have been wonderful molecules that we were able to also generate. And of course, the mechanism of this process in some ways mirrors what we saw before, which is this capturing of this vitrionic control that is allowing us to avoid oligomerization. Then there are also some other methods that we have developed, and I would say that this particular one is especially useful because now what we have is a way of placing heterocycles as opposed to amino acids in the framework of a cyclic peptide. This is done in the presence of this particular reagent we call pink, and Professor Ramazani actually in Iran has done some really, really nice work with this reagent. I don't have time to talk about this, but we can now take a wide range of commercial aldehydes and incorporate them in these rings. And so this is the crystal structure. Other people have used our chemistry, and for a number of let's just say goals. One of them is to understand the cellular permeability of macrocycles. And so these are some of our oxidizal systems, and David Fairley from Australia has put forth a very intriguing concept of how cellular permeability, in other words, ability to go through cell membranes, correlates with certain hydrophobic surfaces and patches on some of our rings. That was a very interesting application. But in our lab, what took place over the last several years was this idea of creating a fairly large collection or a library of these macrocycles and studying their properties. We utilize this tool that is called principal moments of inertia. And, you know, it's a computational tool that allows you to quickly understand what is the overall shape of your molecule. And the reason this is important is because some of the partners that we have had from the industry who are interested in novel molecules, they constantly talk about shape diversity. So you want to make sure that the scaffold is capable of occupying various types of shapes. And this allows you to do that, this particular method, because your molecule can be either disc-like, rod-like, or sphere-like. But the reality is that they're all in between. But the question is, are they primarily, you know, spherical or rod or not? And so if you have distribution that's in the middle, that signifies that there's a lot of diversity in terms of shapes in your molecules. And this is a good thing. Okay, but here is an example that I would say really launched our interests in this area from a new perspective. This is not even a particularly significant compound. What I'm trying to illustrate here is that these two HPLC peaks that have different retention times, some of you might think that these are diastereomers, but the evidence that we have collected was that they correspond to actually conformers. So these are different conformations of the ring that obviously have high barrier to interconversion. And that was a very interesting, I think, experiment that allowed us to ask a number of fundamental questions, such as, what do we know about slow conformational interconversion between macrocycles? And particularly this is, I think, a very interesting and relevant question. you can imagine that bioactive conformation may not correspond to the most stable one. So if this is a stable one, and let's say this is a bioactive, but what if the barrier is very high, such that under conditions where one is evaluating this compound, this molecule is never allowed to get to the state where you desire it to be? I think this can be a big problem, and I think this is fundamentally a very interesting area to study. The way typically people in organic chemistry talk about conformations and energy considerations is through the lens of A values. So I will remind you that A value is the delta G for this process. And it can be, well, it can be estimated, it can be measured, because what you need is you need to have a equilibrium constant and then use this very standard equation, of course. Except the devil is in the detail, as they say, because it's actually very difficult quite often to do that experimentally. And so I'm just going to show you this 1987 paper where the A value of phenyl has been determined. And I think it's a very interesting process that I think maybe convinces you that this is a difficult thing to usually do, and very little energy is needed to perturb this equilibrium. So this is the experimental setup. At 750 degrees, the very hot sample of phenylcyclohexane is rapidly cooled to minus 160. And this is the spectrum that you're going to see in C13. They correspond to axial and equatorial. So you can actually see the axial one, right? Now take a look at this. You warm it up, not to room temperature, but to minus 120, okay? And then you cool it back to minus 160, and you can see that axial completely disappeared, right? So what this tells us is that this, and this is, by the way, the A value, this is the equilibrium constant that you can measure for this particular mixture, and it corresponds to 2.7 kcals per mole. Very little temperature kind of a kick is needed to overcome this barrier. You can see this evidence here. So this is how conformational transitions are really happening. But there's something else that is, you might think, well, this can be useful. For instance, methyl group 174, we can potentially compare it with other types of substituents. The problem is that this is very context dependent. And I think this is in itself very interesting, because if you go to 10-membered ring, you no longer have A value. You see, its delta G here is 0. Moreover, if you go to T-butyl, this is what we teach our students. T-butyl is a so-called locking substituent because it gives you 4.7 kcals per mole if you go from cyclohexane to T-butyl. So you can favor the chair by 4.7 kcals per mole. But look at this case. This is a macrocycle. This is lorlatinib that was developed by Pfizer several years ago. It's an anti-cancer drug. And here, in the, again, context of this much larger ring, simple methyl group allows you to differentiate between the two diastereoisomers by 8.5 kcals per mole. So you see a very interesting problem here, that what we don't have is we don't have any understanding of system response, you see, because you can do very much a big change using small group in macrocycle as opposed to 4.7 by large group in a simple ring. And so what we did then, when we realized this, we went to the literature, and it has been difficult to find these examples because nobody actually pays attention and stresses this. But for us, this is very interesting because, for instance, you see here, these are examples where a very simple change in a stereochemistry of one center resulted in complete reorganization far away. Again, this happens because of, hindered rotations, in incomplete rotations. I think this example is particularly interesting. If I ask students, do you think that the two diastereoisomers are going to be different in conformation? I don't think anybody will say that they will be, right? Because it's kind of a small little stereocenter, but they are extremely different far away from the chiral center. You see this area versus this area. And there are some other examples. And so this actually presents a kind of an intriguing question. And I call it butterfly effect, where, fairly small changes might result in fairly large outcomes far away. I think from this fundamental understanding of biological activity, it is a very central question to be in a position to predict these complicated properties. Effectively, what you do is then you rephrase this and ask the following question: if these differently sized circles represent different barriers for different rotatable bonds, how does a sequence of rotatable bonds or rotors behave that when you take it away from equilibrium? That's a very fun, very much unanswered question. And that, of course, suggests that, you know, if you can answer this question, if you can tackle it, maybe there are conformations of a given system that we otherwise are not able to obtain. And this is a tantalizing opportunity. So in our lab, we have, over the years, in order to address these questions, we have had to learn a lot of NMR, and I will not go through all of the details here. I just wanted to say that we now have a fairly robust system that allows us to, you know, for a given macrocycle, determine connectivity through standard methods. Then we get estimation of angles and long-range constrained distances through these methods, and then we end up with a first initial guess that we subject to molecular dynamics, and then we go through this process again to optimize the structure. And this RMSD, root mean square deviation, is ultimately the parameter that allows us to kind of differentiate structures that are well folded and not. For instance, you see this is a very rigid structure, 0.5. This is much more floppy, 1.7. And this is done in DMSO, 100 nanosecond molecular dynamics. And so the question then becomes, which experimental tools we have to capture unusual conformation. We developed this concept of dominant rotor. A dominant rotor is the following very simple idea. You see, if this is, let's say, macrocycle of some kind, predominantly composed of amides. So each one of these circles represents a different amino acid amide, and you know that it's around 20 kcals per mole, the rotational barrier. And now the question comes, what if we're going to place a dominant rotor, which has a much larger barrier than everything else? What happens to the system? Now, I think that everybody agrees that it will divide the system into two wells, right? To the left and to the right of this dominant rotor. And it's a very interesting question, what actually happens in both of these wells. So in order to take a look at this, we in fact went to medicinal chemistry literature, because there's a lot of very good examples of biaryls, as we all know, and there are many barriers that you can dial in and study. And so we focused on this particular triazole system for the ease of synthesis. And in fact, it is a very simple compound to make. We start with anthranilic acid. It's very simple condensation and another condensation. Racemic form, by the way, becomes important later on. And these are some of the derivatives that we made. So with this amino acid that has this dominant high barrier in hand, Diego, who is currently doing his postdoc with Eric Jacobson at Harvard, what Diego did is he incorporated it into linear compound, linear peptide, and then he heated it to the temperature that typically corresponds to crossing this barrier for rotation. And as you can see, there is no difference after 3 hours of heating. The spectra hasn't changed. So the energy of these two is the same. There is no difference. However, now we incorporated this in a macrocycle, and something interesting took place. We're looking at these two diastereoisomer methyl groups. So they are yellow and green. This is when we start. Then when we wait for 10 hours, you can already see the enrichment, meaning that one of these forms is more stable than the other. But most interestingly is when we cooled down to room temperature, we preserved the equilibrium that we set at high temperature. So that in itself is, of course, due to the fact that we have a dominant rotor and it doesn't allow the system to cross back. But the question is, how different are conformations on the left and on the right-hand side of this dominant rotor in these two wells, if you will. So in order to compare conformations in a visual form, we turned to Ramachandran plots that allow you to rapidly plot these phi and psi angles around a given amino acid residue. And so you can see, for instance, this is the simplest cyclic peptide, diketopiperazine, and it's very much a rigid system. These are allowable angles. You can't really go very far. Now, as you start to increase the size of the ring and you continue looking at the dihedral angles of this phi and psi case and you plot them, you can see conformational diversity, right? The allowable angles are now in different areas. Okay, and so I will not go through all of the details. These green sort of blobs represent molecular dynamic simulations that are starting from the NMR structure. So we analyze each angle, and this is our control. This is all amide system. This is D pro, L pro, and this is our dominant rotor. And I guess you'll have to sort of believe me when I tell you this, but this particular one is a very unusual combination of angles for these amino acids. And so what ends up happening is through the action of this dominant rotor, this extra barrier, we are able to create constrained systems that are on one hand stable, but on the other hand, they're very unusual in terms of three-dimensional presentation of substituents. And that can be hugely important from the standpoint of generating new biological activity. Actually, there are isolated examples in small molecules that I call landscape remodeling. And these are interesting cases that correspond to unusual conformations, but they're very, very rare. For instance, if you put 4 cyclohexyl groups on cyclohexane, the most stable form is going to be twist boat, which is, I think, very interesting because we typically do not expect twist boat to be stable, but it's, of course, a kinetic stabilization. The barrier to undergo transformation into a boat is very high. I already covered this example. This is a beautiful demonstration in a small molecule where the preferred form is axial. And here is another case of this axial preference. So coming back to our systems, how different are these whales, should we say? Well, and I think that there are instances, there are cases that we have studied that are really, really unusual. For instance, if you consider these two forms, this is R and S, these are basically diastereomers. We call them whales because it's left and right hand side with regard to big barrier that is set by this biarrow. But you can see polar surface area is dramatically different. For instance, one of these, this guy does not dissolve in methanol. For a cyclic peptide, this is fairly unusual. The other one, of course, dissolves very well. Why is this? It's because of the particular network of hydrogen bonds, excuse me, that we change in one of these conformations. And so you can actually take a look at this data. This is HD exchange at 298 Kelvin. And so very different T1 half. You can see for yourself right away how different one proton can be. And that, of course, represents a huge change in polar surface area. Now, the chemistry itself has enabled us to freeze conformations that are on one hand different, but on the other hand, and that's from my perspective is the most interesting part, they differ only by a very small amount of energy. So, I mean, it's actually kind of ridiculous, right? If you think about it, to ask a question of isolating two molecules that differ by 0.5 kcals per mole. Well, I don't think it's possible because, of course, at room temperature, we have about 20 kcals per mole of thermal energy. It will level everything, right? But in our case, because of this barrier, we can actually encounter these counterintuitive situations where we have this very unusual conformation that is on one hand stable, but on the other hand, differ from the other one only by 0.5, right? And it's because of the barrier that it actually can exist. And so on the subject of potential fundamental interest of some of these structures, the so-called type 2 alpha RU turn. And this is simply, it's a combination of dihedral angles that represents that particular turn. It's a very rare motif. It's conformationally very constrained. And so only 2.5% of all proteins in protein data bank, they display this motif. And yet we are, in fact, able to freeze this motif. I'll skip through this slide. I'll just go to this one to illustrate to you an additional sort of an interesting point. So this is the kind of in terms of the differentiation, this is the best number that we have so far, 32. So it corresponds to 2.06 free energy difference between these two molecules. They are separable, okay? It's not really a mirror image. It's just to illustrate that they are very different in terms of the three-dimensional presentation. But I just want to, again, to emphasize the significance of this number and kind of put it in perspective for you guys, what this might mean. And so the analogy that I'm going to give you is a CF3 group. It's a very similar A value, this delta G between axial and equatorial. So because we are able to separate and study these unusual conformations, it's kind of similar to me telling you that I'm going to give you a liter of axial CF3 containing cyclohexane, which is, of course, kind of ridiculous, right? But that in effect is what's happening through the action of dominant rotors. These are nicely folded structures, as you can see. And again, always keep in mind, please, so how little energy is actually needed to shift something that is actually 2.7. It takes you heating from minus 160 to minus 120, and it is completely gone. We have, since then, added this element of what we call composite barrier. So what does that mean? It's a change in the rotational barrier that you can potentially imagine through the action of substitution that is somewhere nearby. And so this is the dominant rotor with an extra methyl group that is placed in the ortho position. It's actually kind of difficult to even conceptualize how you would think about this barrier change because it's not directly on the biaral axis. But the net result is actually kind of interesting. And this increase in barrier that we can actually measure corresponds to the emergence of, as you can see, you don't really need to see three-dimensional view to appreciate the fact that these two are very different conformations in terms of the allowable dihedral angles. And I will finish up with the continuation of this concept that now takes on organic chemistry and involves reactions. So when we think about a barrier in itself is a three-dimensional event, right? Because you are usually rotating around a given bond and it is happening in 3 dimensions. We ask this question, can we think about barriers in 2 dimensions? Meaning that there is going to be some kind of a reversible, hopefully structural change, but we're not going to allow the system to rotate. We're going to only allow it kind of like this windshield wiper on the car during rain. And again, ask the question, what happens with the rest? And this is, I would say, a completely untouched area from the standpoint of conformational analysis, asking this question of these 2D transpositions. So Shinya Kobori, who was a postdoc and he went back to Japan now already a year ago, he decided to tackle this using the so-called Bolton-Katritsky rearrangement. And Bolton-Katritsky rearrangement is if you have the elements of oxodiazole and nearby amide. And you see this oxygen can actually attack this nitrogen such that you regenerate oxodiazole on the other side of the ring, and amide now emerges on the opposite location. You see, this amide goes here. It takes about 24.6 kcals per mole in the context of a macrocycle. So that was a very interesting result to us because we studied this by NMR. And one of the things that you can tell right away is the significant difference between how rigid is one form versus the other. And usually right away, even without any complicated 2D NMR, if your chemical shift is spread, this is a much more rigid structure as opposed to the other one. But what became particularly interesting when we analyzed these compounds, both of these wells in each case, and we compared with standards that are simple cyclic hexapeptides. So you see they overlay well, except both forms tend to produce cis-amides, and cis-amides are rare. Cis-amides are very important in the area of, for instance, kinase activity and so on and so forth. And so the fact that we are able to stabilize very unusual cis-amides, I think, is particularly interesting part of this project. And so these, we call it two-dimensional events with interesting three-dimensional outcomes, because the rest of the system reorganizes quite substantially during this reaction. And so you can now imagine using organic reactions as barriers, right? So, and this is, I think, kind of an interesting possibility, because there are so many reactions. Not all of them are going to be useful for this, but the barriers are tunable. And I already showed earlier that there is a tremendous set of possibilities for unusual conformations with interesting barriers. I'm going to just charge my computer 1 second and continue the presentation. Okay. Another reaction that we are studying in the context of these two-dimensional barriers is the so-called Cornforth rearrangement. And Cornforth rearrangement is very much similar to Bolton-Kotritsky, but it actually introduces the emergence of this isonitrile from an oxazole. And so I would say that Cornforth rearrangement is, for all intents and purposes, not really a useful process synthetically. It has not really caught on because it's not really easy to see where and why somebody would be inclined to study this rearrangement. But in the context of a macrocycle, this structural change allows us something that we were never able to do before, to go from ring with n atoms to a ring with n-1 atom. And that is a very, very subtle change that is possible during this rearrangement. And we are very much investigating this as an active project right now. One of the things that we can say already is that we can have the switch between beta turn and gamma turn in some of these structures. And again, it's DMSO, it's 120 degrees, and this is how this rearrangement is taking place. So it's a fascinating, I think, consequence of how simple reactivity allows us to fine-tune the three-dimensional properties of some of our compounds. And so with that, I'm just going to maybe pose a thought-provoking, I hope, a question that I think to some extent I answered. And that question is, when we think about chemistry space, the available chemistry space is, of course, enormous. You all have heard numbers, 10 to the 63, there's not enough carbon in the universe to make all molecules within 500 or 1,000 molecular weight. And I think that we are trying right now to rephrase this from a slightly different angle. And this angle is actually, it's even bigger. And probably we would be able to access unusual properties, but without making completely new molecules, but rather making new conformations of known molecules. And so we call it conformational polymorphism. And the question is, does it exist? I think it definitely exists. Usually it's in the noise, because the energy that is thermal, that is available to us, levels everything. We never stop at unusual conformations. And I hopefully was able to show to you, especially in the latter part of my talk, that there are synthetic constructs that allow us to generate unusual conformations that are stable and can be studied. And so with that, let me thank a group of very dedicated students and postdocs. This obviously is not a very recent photo because nobody is wearing masks, but I mentioned some of the key group members during the talk, and I'm really grateful for their dedicated efforts, as well as a number of funding agencies who have contributed to our research program. So I would like to thank them, and I would like to thank you, and I would very much be interested in, of course, visiting in person Istanbul and seeing how everything works there. Thank you very much.
Andrei, thank you very much for this very nice, deep, and exciting and energetic talk. It was a great pleasure to listen to this talk. I think everybody thinks like that. So now we can take questions. Yes, please ask questions, send in a message or just by raising hand. Andrei, can you read this question on chat? Or?
Yes, yeah, I can read. So,
please.
Also employ electronic structure. Yes, right. So, so the question is about whether or not we can employ calculations to have a better understanding of conformational transition. Yeah, this is a very good question. We have not done a lot of this, and the reason is that it's actually very difficult. So ab initio calculations, we have collaborated with some people, and it's tough. So at this point, it goes sort of hand in hand with experiment, but I think at some point when we learn more, I think it will become more important. That actually is a very also interesting point from the standpoint of machine learning, because a lot of people also ask me this question about machine learning and maybe using calculations to predict. And the quality of these predictions, unfortunately, right now is not so high because it's so difficult, right? But I think that it should become possible. I just don't think it will be easily done using DFT calculations, I think. Just too expensive.
More questions, please. Andrei, what can you say about application of this very powerful tool in terms of drug discovery and novel drug discovery?
Right. Well, so the application right now that we are conceiving and some other people are collaborating with us on is in the area of, you see, if you make a cyclic peptide, you are producing usually one conformation. Sometimes they're floppy, so there are many. But the problem is that quite often you can generate the wrong one, the one that is not biologically active. And so you have to very carefully fine-tune it, and we don't have tools for that. And so this offers one such tool where if crystallographic data tends to demonstrate that you need to have this unusual angle between two amino acids, then you can explore some of this conformational fine-tuning that I showed using chemistry to arrive at the precise understanding of the right conformation. So the big problem in terms of our ability to use it in drug discovery is that still it's difficult to make these compounds. So we cannot make too many of them. Excuse me. So, but structure-driven and very much X-ray crystal-driven problems are definitely doable because you don't have to make many compounds for that. Yeah.
Thank you. Another question is, as I can understood, the geometrical configurations or structure plays this very important role. So can one imagine a preferred geometrical structure in this crystallography or this conformation structures? Some preferred structure, for example, you know there's some preferred geometrical structure. Or does topology make sense in this?
So, you know, it's interesting, right? Because, for instance, there is an estimation that was published by Perola. That's a name of an industrial person from, I think, from AstraZeneca, that 60% of drugs do not bind their targets in ground state conformation, which is, I think, important because when we as chemists, when we think or design or draw something, we always tend to rely on our understanding of what is most stable, right? This is for us the most important thing. But it turns out that there are so many important drugs that interact with proteins in high energy conformation. And well, that I think is a very important finding, because if you can help the molecule reach high energy conformation, if you can already present it in a high energy conformation, you don't have to pay the price, the cost of readjustment, because that sometimes is why molecules fail, that it takes them very long time to find the right conformation. You know. Yeah.
Thank you. More question, please.
There's another question.
Yeah.
Philosophical, how would you differentiate a stable conformation versus a stable configuration in biaryl? Yeah, it's an interesting philosophical question, I think. I am not sure. I don't know. I'll have to think about this. How would you differ? Because, you know, I would say that configuration ultimately is also conformation, right? So, yeah. Stable. I think that stable configuration of a biaryl, this is one of the things that we have found, is it determines the rest of the system conformationally. But actually, on this note, one of the things that we are now studying, and this I think maybe to some extent addresses this question, is we're trying to come up with systems where we have a dominant rotor, meaning that it's a very big barrier to rotation. And then in the other part of the molecule, we have also biaryl, but with a very low barrier to rotation. And I think that could potentially answer your question, because we actually do not have yet the rules or understanding for how one biaryl influences the other biaryl. And so if we can enforce with a high barrier the configuration of another biaryl on the other part of the ring, I think that in principle could be very interesting. Yeah.
More question, please. Our people here indeed very shy to ask questions.
No problem.
Yeah.
Maybe, yeah. Maybe when we do in person, we can.
Yeah. They shy, but one start, impossible.
Yeah, for sure.
To stop them. So, Andrei,
yes.
If you don't mind, please give your final comment and we can close the session after your final comment. If you have some final remarks.
Okay, well, so I think that I really enjoyed interaction. I very much value this opportunity to be in my living room and then have a chance to present in front of an audience in Turkey. And again, I have never been to Turkey, so I really would like to go to Turkey. You know, I have a lot of friends who have been there, but I have never been. So definitely. I really like the food from that region as well. So,
so that will be a pleasure. So we will be very happy to have you in our summer school workshop or just visiting. So I think we will have many discussions in person when you visit us. So let us wait for the time being for that case.
And maybe when I visit, I can describe some of our boron chemistry, which is a very big other part.
Yeah, sure.
And if anybody has any questions that are maybe they have to think about how to formulate, you can always email me. That's not a problem at all.
Oh, thank you so much.
Yeah.
This is very nice, and we appreciate this very much. So we can perhaps stop here. So thank you once again very much.
Thank you.
That was a pleasure for us, and was a pleasure to see you.
Thank you. Thank you very much.
Okay. Bye.
Bye.